Hi, Intro to Geometry. While we're on home instruction, we're going to try to cover one unit. So we're going to look at Unit 10, which is all based on similarity. Today's topic is ratio. And this is the note packet that you're going to need to go through the lesson. All packets should arrive on Monday, March 23rd through the bus route. All right, so a ratio is a comparison of two numbers by division. Basically, it's a fraction. We have different variations that we use when we look at ratios. The first is using the colon. This is read A to B. If you don't like using the colon, you can actually write the word to. We still read it A to B. But the most popular is the fraction, and we still read it A to B. When you write a ratio, we are going to write them in a definite order. Usually the verbal directions will talk about what value needs to come first and then which value needs to come second. We want to maintain that order when we write our own fraction. Because we're working with fractions, you should reduce all of your ratios to lowest terms. The directions may not tell you to do that. You're just expected to reduce it, just like any other fraction. When you write a ratio, you have to have the same unit of measure on each element that's being compared. Remember, you can stop the video at any time if you need to catch up on your notes. In our first example, we're comparing 3 centimeters to 15 millimeters. We can see that the metric unit is different. I find it's always easier to convert the larger unit of centimeters into a smaller unit of millimeters. So we've worked with the metric system before. We're going to move our decimal one place to the right. And when we do that, we end up with 30 millimeters to 15 millimeters. Now that they're in the same unit of measure, we're going to reduce this to lowest terms. Both have a common factor of 15. So in its simplest form, the ratio is 2 to 1. I did leave it in this format because that's how it was presented. In our next example, we're comparing $1 to 1 dime. Again, these are not in the same unit of measure. Think about how many dimes would be present in a dollar. I know that there's 10 dimes in a dollar. So now that they're in the same unit of measure, I can reduce this ratio to lowest terms, and it's still 10 to 1. On the last slide, we were comparing two numbers, but it is possible to compare more than that. What we will write is called a continued ratio, and it is a comparison of 3 or more quantities. Whenever you have a continued ratio, there should always be a constant of proportionality that exists between all the ratios. We use the variable k to represent that constant, but basically it's a scale factor. It tells me that there's a certain ratio that all values should maintain. This is an example of a continued ratio. It's written in a horizontal format. What you can see here with the red bracket is that the first element A is being compared to the first element D. And then with the green bracket, the middle element B is compared to the middle element E. And then with the blue bracket, C is compared to F. This format is not really helpful when you're having missing values that need to be found. So it's easier if you convert it to a vertical format. This is something we're more familiar with. These are all 3 sets of ratios, and they do look like they're in a proportion format, so we could solve for anything that we need to. Again, A is still compared to D, red bracket, B to E with the green bracket, and C to F in the blue bracket. So this example, we have a continued ratio, 4 to 10 to 12, and that's the same as 2 to x to y. So what I'm going to do first is put it in that vertical format, and this is what it would look like. So the first elements second elements and third elements are all lined up. Then what I'm going to do is I'm going to notice that this first ratio, 4:2, that is my constant of proportionality K. That tells me that all the remaining ratios, 10 to X and 12 to Y, need to be in a ratio of 4:2, which is really 2:1. So I'm going to ignore the last ratio, 12 to Y, and I'm going to strictly deal with the first two. This is a proportion, which we've solved before. We're going to cross multiply 4 times X, and that should equal 2 times 20. When I do the cross multiplication, I'm going to get an equation where 4x equals 20. And then to get x alone, we'll divide by 4, and we realize x is 5. When you compare that, 10 to 5 does reduce to 2:1, and I've maintained the ratio or the constant of proportionality of 4:2. Now I also need to solve for y. So I'm going to cut out the middle ratio of 10 over x, and I'm going to do the same thing. I'm going to cross multiply 4 times y and 2 times 12. You can see the equation 4y equals 24, and then to isolate y, we're going to divide both sides by 4, and y is 6. And in that final ratio, we have 12 is to 6, which reduces to 2:1. So all three ratios are the same, 2:1. Let's look at our first word problem. It says angles 1 and 2 are supplementary, are in a ratio of 2:7. Notice how they said angle 1 first? That part of the ratio is 2. 2 parts belong to angle 1. And they mentioned angle 2 second. That's the second part of the ratio, 7. 7 parts belong to angle 2. So what I'm going to do first is write two let statements like we did in algebra. Angle 1 is represented by 2x. X is some multiplier that will tell us how to change our angle measure so that I maintain the ratio of 2:7. And the second angle, angle 2, is represented by 7x. Because I know that the angles are supplementary, I'm going to write an equation where I show that the angles add up to 180 degrees. I'm going to combine like terms on the left-hand side. And then to find x, I'm going to divide both sides by 9. So the value of x is 20. Now that I know what the multiplier is, I can sub into both of my let statements and find the values of angle 1 and angle 2. And there's angle 1, it's 40 degrees, and angle 2 is 140. And again, you can do a mental check, but those add up to 180 degrees, which is supplementary. In our second word problem, they're saying the measures of the angles of a triangle are in a ratio of 9 to 4 to 5. We know that the angles of a triangle add up to 180 degrees. So the first thing I did is I drew a model instead of writing let statements. And then remember, we want to maintain the ratio 9 to 4 to 5, but there is some kind of multiplier that's not there, and we'll add an x onto each of those parts of the ratio. So the angles are now 9x, 4x, and 5x. I'm going to write an equation to show that the sum of those angles is 180 degrees. All my like terms are on the left. When I combine them, I have 18x equals 180. And then we'll divide both sides by 18, and that means x is 10. The last part of the question says to find the measure of the angles. So again, I'm going to sub into 9x, 4x, and 5x. And right here you can see the angles are 40, 50, and 90. If they ask you to classify the triangle based on its angles, the 90-degree angle will be controlling that. So this would be a right triangle. For the last part, we're going to write ratios based on the description that they provide. So in number 1, they're talking about shaded parts to all parts. So the all parts is important. All parts is listed second. The number 12 is listed second, so I know that there's 12 parts in my diagram. So what I did is I drew a rectangle, which is a 3x4, so I can see there's 12 boxes. And then I'm going to shade 5 of them so that I can maintain the ratio of 5 to 12. In the second example, it says shaded parts to unshaded. That means I'm going to have two separate quantities. The grand total then is 5 plus 12, so there's 17 parts. When I draw my diagram, you can see I have 17 boxes. So shaded is listed first as well as 5. We're going to shade 5 boxes, and that should leave 12 unshaded. So you can see in my diagram, I've modeled 5 to 12. For the next section, they just want us to write the ratio in simplest form. What you can do is use your TI Nspire calculator app and enter the fraction or the ratio into the calculator, and it will find the common factor for you and reduce it. So 8 to 36 has a common factor of 4. It should reduce to 2 over 9. So what I'm doing is essentially dividing the numerator and the denominator by 4. Same thing with number 4. The common factor there, you could use 4, you could use 6, but it's even better if you go with a bigger factor of 12. So if I divide both by 12, the resulting ratio is 2 to 3. In number 5, they're using a horizontal format. If you don't like this format, you can make it vertical like problems 3 and 4. 45 is your numerator, 60 is your denominator. But again, the common factor is 15. So I'm dividing both pieces by 15, and the resulting fraction is 3 to 4. Number 16 is similar. So the common factor there is 4. I divided both pieces by 4, and it leaves me with a reduced ratio of 4 to 5. For the last two problems, number 7 and number 8, they're making a comparison between two quantities that are not in the same unit of measure. So again, the centimeter label, it's better if you convert that to millimeters. So we're going to move our decimal one place to the right. So what we're comparing is really 8 millimeters to 20 millimeters. And again, we're looking for a common factor. So they both have 4 in common, and I'm going to divide, and a reduced ratio of 2 to 5 is present. Once they're in the same ratios measure, you can drop the label. So the final ratio doesn't have a unit of measure. In number 8, I know that 2 quarters is the same as 50 cents. So we want to know how many dimes are in 50 cents. So I know that's 5 dimes. And now that they're both in the same unit of measure, I can drop the label and reduce. And ultimately the ratio is 5 to 3. This is homework number 96. This will be in your packet. If you have any questions, please make sure you give me a call. You can call my home number first. If I don't answer, you can try my cell, or you can text me on my cell, or you can just send me an email. Have a great day.